inverse trig functions and their derivatives. All right, so hopefully when you took your trig class, you learned a little bit about the inverse trig functions, arcsine, arccosine, arctangent. I'm going to remind you about them today, the bare bones knowledge. If you feel like I've never seen these before in my life or I have no recollection of them, then you should go back and review more of the details of these functions. But I'm going to give you the highlights of them here. All right, so we're going to start by looking at y equals sine x. And the graph of y equals sine x, if I draw a picture of one period or one cycle of this function starting at 0 and moving off to the right, then I've got marks that are important. For example, I've got my top of the hill at pi over 2. I've got an x-intercept at pi, bottom of the valley at 3 pi over 2, and another x-intercept at 2 pi. And then I can repeat this cycle off to the left here. And so I have corresponding angle labels on the left, but they're negative. All right, now when we look at y equals sine of x, then when I write that out, y equals sine x, the input into the sine function, that's the x value, that's an angle. And so our input is an angle, and the definition of sine is opposite over hypotenuse, or ratio. We can think of it as ratios of sides of a triangle. And so when we input an angle, the output that we get, the y value, the output is a ratio of sides of a triangle. I mean, we can also think of this, if I think about my trig function as y values on the unit circle, then the output is a y value on the unit circle as well. Okay? But the input is an angle, and the output is a ratio of sides. Now, what this section is about is the inverse trig function. So it's not that we really want to deal with y equals sine x. We want to deal with the inverse function. And so remember that when we talk about an inverse function, what we're doing is taking the diagonal line y equals x and reflecting our function across y equals x. Here is y is equal to x. But one issue that we have with the sine function is the sine function is not one-to-one. It does not pass the horizontal line test. So if I reflect this curve across the diagonal line y equals x, then I'm going to get a zigzag that goes up the y-axis. It won't be a function anymore. And so what we have to do is we have to restrict the domain of y equals sine x so that when we draw a picture of the inverse function, we actually get a function and not something that fails the vertical line test. So here's what happens. We really only care about, and maybe I'll use a green marker here, we really only care about the region of the sine function for angles that start at negative pi over 2 and end at positive pi over 2. And so we are really just taking this short segment of our sine graph. Now some other labels on this should be that our y values go from -1 to +1. And so when I look at y is equal to inverse sine of x, or also called arcsine of x, then my picture is going to take my x-axis values from negative pi over 2 up to positive pi over 2 and make those into my y values. So we have negative pi over 2 up to positive pi over 2 on the y-axis. And our y values from the original function now become our x values on the inverse function. And so this green segment, when we reflect that across the y equals x diagonal line, we end up with a picture that looks something like this. And this is a picture of our arcsine function. So when I look at the arcsine function, the input and the output are swapped. Okay? In the original function, the input was an angle, and the output was a ratio of sides. Now, on our arcsine function, the input is a ratio of sides, and the output is an angle. And in particular, the output angle that we get is some angle between negative pi over 2 and positive pi over 2. All right, so the domain of this function is the interval from -1 to +1, and the range of this function is the interval from negative pi over 2 up to positive pi over 2. All right, are there any questions about the arcsine function? Will?
So how would this relate to the derivatives? Like, it doesn't seem like you really get a straightforward derivative with the arcsine.
Well, so the arcsine is not a derivative of the sine function.
Well, taking a derivative of the arcsine.
Yeah, so that's really our next question is, okay, so in trig class you learn what this picture looks like. In calculus, what we're interested in is what is the shape of this curve? How steep is this curve y equals arcsine x? And we really only are talking about a derivative where the x values are only legitimate from -1 to +1. Okay, but we can still talk about the slope of this curve.
At 0, does it have a tangent with a slope of 0?
So what's happening at 0? Well, if we check the y equals sine of x graph, then the slope when x is equal to 0, if I do y prime is equal to cosine of x, and so y prime evaluated at 0 is cosine of 0, which is 1. So the slope here is 1. So our tangent line here at 0, 0 actually exactly lies on y equals x. So this is actually probably, this is a little bit of an erroneous picture because this should really come up through here, and here at this point should still have a slope of exactly 1.
Okay.
So yeah, so that's really a little bit more legitimate, something like that. Good question. Okay, other questions? All right, so our big question that's coming up now is, okay, here we've got a function, and this function is differentiable. There's no corners or cusps going on here. So I'd like to have a formula for the derivative of y equals arcsine x. So if f of x is equal to inverse sine of x, then f prime of x is equal to something. And we're going to figure that out. All right, so we've got y equals arcsine of x, and we'd like to be able to come up with a derivative for arcsine of x, but since I don't know a derivative for the arcsine of x, I can't just write it down. So what I'm actually going to do here is, if y is equal to arcsine of x, if I take the sine of both sides, then I've got sine of y is equal to the sine of inverse sine of x. So on the right-hand side, my sine and its inverse, they leave me with just an x. And so I have sine of y is equal to x. And now I've gotten an equation where y is defined implicitly as a function of x. So I can look at this equation, sine of y equals x, and do implicit differentiation. All right, so on the left side, I've got sine of y, so its derivative, thinking y as a function of x. On the left side, we've got sine of y. So its derivative will be cosine of y times the derivative of y, which is dy over dx. And on the right side, the derivative of x is 1. All right, are there any questions about that so far? Okay. So now we can solve for dy over dx, and we get dy over dx is equal to 1 over cosine of y and this is a fabulous formula. Okay, the derivative of y with respect to x is equal to 1 over cosine of y. It's kind of fabulous. It's cool because it's nice and clean, but normally we want our derivative to be a function of x, and right now our derivative is a function of y. And so this is a little bit of a problem. This is almost cool. Okay. The problem is that our derivative is defined in terms of y, and we want our derivative defined in terms of x. And so the way that we're going to deal with this is that we're going to make a small change here. Okay? Cosine of y, we'd like to deal with that. So rather than having cosine of y, what I'm going to write down is I'm going to note what is the best, number one, absolute, most fabulous trig identity in the world?
Cosine squared x plus sine squared x equals 1.
Yes, cosine squared x plus sine squared x equals 1. I hope you all have that tattooed somewhere on your body. Okay. The same is true if I use y. So cosine squared y plus sine squared y is equal to 1. All right, so if I take this equation and I solve for cosine y, I have cosine squared y is equal to 1 minus sine squared y, and I can take the square root of both sides. And I get cosine of y is equal to plus or minus 1 minus sine squared y. All right. Looking at what I have here, I'd like to be able to write this in over here. The problem here is that I've got a plus or minus in front, so I have to choose between the plus and the minus. And here's how I think about this. On my y equals inverse sine of x function, my y values are angles between negative pi over 2 and positive pi over 2. And so possible angle values for y are angles between negative pi over 2 and positive pi over 2. So in terms of the unit circle, that means that we're looking at angles that occur in quadrant 1 and quadrant 4. And in quadrant 1 and quadrant 4, cosine of those angles is always positive. So up here, we're going to be choosing the positive version of our square root. So in quadrants 1 and 4, cosine of the angle is greater than or equal to 0. So we're going to choose the plus rather than the minus. All right, so let's go back over here to dy over dx is equal to 1 over cosine y. And I'm going to replace cosine of y with square root of 1 minus sine squared y. This doesn't look any better. In fact, it looks a lot worse. Okay? Not only do we have y's involved, but now I've made it even more complicated. But we've got one last step. It's going to make, hopefully, everybody happy. So here I've got 1 over square root of 1 minus sine squared y. By the way, sine of y equals x. And so if I have sine squared y, I can replace that with x squared. And so in the end, we've got dy over dx is equal to 1 over the square root of 1 minus x squared. Wow. So there was a lot of cleverness that went into this, right? I mean, number one, we started out with y equals inverse sine of x, and we rewrote it so that we have sine of y equals x. Then we used implicit differentiation, came up with a formula for dy over dx, and then used some clever trig identities to change this cosine of y into something in terms of x. So in the end, if f of x is equal to arcsine of x, and f prime of x is 1 over the square root of 1 minus x squared. And so this is our derivative rule for arcsine. All right, so please find a neighbor near you and do rock, paper, scissors to decide who's going to tell who about this derivative rule. You have 20 seconds.
The derivative of arcsine is 1 over the square root of 1 minus x squared.
Yeah, right, buddy. Okay, so
If f of x sine
the derivative of x prime of x. I agree.